Tonight, we're going to witness something no human will ever see. We're going to travel further into the future than your mind can possibly comprehend, to a time so distant that the numbers describing it have more zeros than there are atoms in your body. We're going to find the last star that will ever shine in this universe. A tiny, dim, red ember burning alone in an ocean of absolute darkness. Every other star will have died. Every galaxy will have gone dark. The universe will be cold, empty, and silent. And there, in that incomprehensible loneliness, one final star will glow, the last light in existence. By the end of this journey, you will understand why this lonely survivor matters, and why its death will mark the end of an era that began with the Big Bang itself. Before we dive into this incredible journey through time, if you find these explorations of the cosmos fascinating, a quick like or subscribe would really help this channel grow. It's a small gesture, but it makes a huge difference for me. I appreciate every single one of you who joins me on these adventures through space and time. Now, let's begin. Let's start at the beginning. Not the beginning of time itself, but the beginning of stars. Because to understand what the last star will be, we first need to understand how stars live and how they die. Right now, as you listen to these words, somewhere in the universe, a star is being born. Deep inside a vast cloud of gas and dust, perhaps hundreds of light years across, gravity is slowly and patiently pulling matter together. These immense clouds are called nebulae, and they serve as the nurseries of stars. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is one of the closest stellar nurseries to Earth. Inside it, at this very moment, new stars are forming. The process begins when a region of the nebula becomes slightly denser than its surroundings. Maybe a nearby supernova sent a powerful shockwave rippling through the cloud. Maybe the gravitational tug of a passing star created a disturbance. Whatever the initial cause, once a region becomes denser, gravity takes over completely. The dense region pulls in more gas from its surroundings, becoming denser still. This increased density attracts even more gas. It becomes a runaway process, a cosmic snowball effect. The region collapses inward under its own immense weight. As the gas falls inward, it heats up. This is basic physics at work. When you compress a gas, it gets hotter. Think of how a bicycle pump gets warm when you're pumping air into a tire. The same fundamental principle applies on a cosmic scale, but with far more dramatic and spectacular results. At first, the collapsing cloud is just warm, then it becomes hot, then very hot. After perhaps 100,000 years of continuous collapse, the core of this cloud reaches temperatures of about 10 million degrees. And at 10 million degrees, something truly magical happens. Hydrogen atoms in the core are moving so fast, colliding so violently, that they overcome their natural electrical repulsion and fuse together. Two hydrogen nuclei, each consisting of just a single proton, smash into each other with such force that they stick together. This creates a heavier element. Eventually, through a complex series of nuclear reactions, 4 hydrogen nuclei combine to form one helium nucleus. But here's the crucial and remarkable part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that created it. About 0.7% of the original mass is missing. Where did that mass go? It became energy. Pure energy, released according to Einstein's famous equation, E equals mc squared. That tiny bit of missing mass, multiplied by the speed of light squared, produces an enormous and almost incomprehensible amount of energy. And this energy is what makes a star shine. When fusion ignites in the core, the energy released creates an outward pressure that pushes against the surrounding material. This pressure pushes against the inward pull of gravity, and for the first time in its existence, the collapsing cloud reaches a state of balance. Gravity pulling inward, fusion pushing outward. The two opposing forces reach equilibrium. A star is born. This delicate balance defines a star's entire life. As long as fusion continues in the core, the star shines steadily. The moment fusion stops, gravity wins. The star either collapses or explodes or slowly fades away. Everything that happens to a star throughout its entire existence, its complete life story from birth to death, is determined by this eternal battle between gravity and fusion. Now here's what determines how long a star actually lives. It's not simply how much fuel it has, though that certainly matters. It's how fast it burns that fuel, and how fast a star burns as fuel depends primarily on one crucial factor: its mass. Massive stars are hot, extremely hot. Their cores reach temperatures of hundreds of millions of degrees, far hotter than our sun's comparatively modest core. At these extreme temperatures, fusion proceeds at a furious and almost desperate rate. A star 20 times the mass of our sun doesn't live 20 times as long as you might expect. It actually lives about 1,000 times shorter. A massive star might have 20 times more fuel than the sun, but it burns through that fuel 10,000 times faster. The relationship is dramatically nonlinear. Our sun will live for about 10 billion years total. A star 20 times more massive might live only 10 million years. That sounds like an incredibly long time by human standards, but cosmically speaking, it's merely the blink of an eye. The universe is 13.8 billion years old. A massive star lives for less than 1/10 of 1% of that time. These stellar giants burn bright but briefly. These massive stars are the celebrities of the cosmos. They're bright, they're spectacular, they're dramatic, and they burn out fast. When you look up at the night sky on a clear evening, many of the brightest stars you see are these massive stars. Rigel in the constellation Orion is about 20 times more massive than our sun. It shines an astonishing 70,000 times brighter. But it will exhaust its nuclear fuel in just a few million years. If Rigel were a human being, it would be a child prodigy who accomplished everything remarkable by age 5 and died by age 10. When massive stars die, they die dramatically and violently. Once a massive star exhausts the hydrogen fuel in its core, fusion doesn't simply stop altogether. The core contracts under gravity's relentless pull, heats up to even higher temperatures, and begins fusing helium into heavier elements like carbon and oxygen. When the helium eventually runs out, the star begins fusing carbon, then oxygen, then silicon. Each successive stage proceeds faster than the one before. A massive star might spend millions of years steadily fusing hydrogen, then perhaps a million years fusing helium. Carbon fusion might last only 1,000 years. Oxygen fusion perhaps just a single year. Silicon fusion proceeds for mere days. The star is desperately burning through heavier and heavier elements, frantically trying to generate enough energy to hold itself up against the crushing force of gravity. But it's ultimately a losing battle that cannot be won. The fusion chain ends with iron. Iron represents the absolute end of the line for nuclear fusion. Fusing iron doesn't release energy like fusing lighter elements does. Instead, it actually requires energy to be put in. So when the core of a massive star fills with iron, fusion stops completely. And when fusion stops, gravity wins instantly and catastrophically. The core collapses in less than a single second. Material falls inward at a significant fraction of the speed of light. The core compresses so violently that the protons and electrons are forced to merge together into neutrons. The collapsing material slams into this incredibly dense neutron core and rebounds outward in a catastrophic explosion of almost unimaginable violence. This is a supernova. For a few weeks following the explosion, a single exploding star can actually outshine an entire galaxy containing 100 billion stars. The explosion scatters the heavy elements that were forged in the star's core. Elements like carbon, oxygen, iron, gold, and uranium out into the surrounding space. These scattered elements eventually become part of new stars, new planets, and new life. The iron in your blood, the calcium in your bones, the oxygen you breathe with every breath, all of it was forged in the cores of stars that died billions of years ago. We are quite literally made of stardust. After the supernova explosion fades, what remains depends entirely on the original star's mass. If the original star was between about 8 and 25 times the Sun's mass, the collapsed core becomes a neutron star. This is an incredibly dense ball of neutrons, perhaps only 12 miles across, spinning rapidly, possessing a density so extreme that a single teaspoon of neutron star material would weigh about 4 billion tons if you could somehow bring it to Earth. If the original star was even more massive, above about 25 solar masses, even the neutrons cannot resist gravity's ultimate triumph. The core collapses completely and utterly, becoming a black hole. This is a region of space where gravity is so overwhelmingly strong that nothing, not even light itself, can escape its grasp. But what about stars smaller than these dramatic giants? What about ordinary stars like our own sun? Our sun is currently about 4.6 billion years old. It's roughly middle-aged for a star of its size. In another 5 billion years or so, it will exhaust the hydrogen in its core. When that happens, the core will contract and heat up, just like in a massive star. But the sun isn't massive enough to fuse carbon or heavier elements. Instead, it will swell enormously into a red giant star, perhaps large enough to engulf the inner planets Mercury and Venus, and possibly even Earth. Its outer layers will eventually drift away gently into space, forming a beautiful expanding shell of glowing gas called a planetary nebula. And the core will remain behind, a dense ball of carbon and oxygen about the size of Earth, but containing the mass of the entire sun. This stellar remnant is called a white dwarf. It no longer produces any energy through nuclear fusion. It shines only because it's still extremely hot from the star's previous active life. Over billions upon billions of years, it will slowly cool and fade, eventually becoming a cold, dark object called a black dwarf. But the universe isn't old enough yet for any white dwarf to have cooled that completely. Every white dwarf that has ever formed in cosmic history is still glowing with residual heat. White dwarfs are essentially the corpses of stars like our sun. They're remarkably common throughout the galaxy. About 97% of all stars in the Milky Way will eventually become white dwarfs. They're small, they're faint, and they represent the final end of the line for medium-sized stars like our own. But there's one more important category of stars we haven't discussed yet, and this category is the most important for our story tonight. These are the smallest stars in the universe, the red dwarfs. Red dwarfs are stars with masses less than about half the sun's mass. Some red dwarfs are as small as just 8% of the sun's mass, barely massive enough to sustain hydrogen fusion in their cores. Below that critical limit, you get brown dwarfs, which are too small and cool to be considered true stars at all. Red dwarfs are remarkably dim. The smallest red dwarfs produce less than 1,000th of the light our sun produces. You cannot see a single red dwarf with the naked eye from Earth, even though they are by far the most common type of star in our entire galaxy. Proxima Centauri, the closest star to our solar system at a distance of about 4.2 light years, is a red dwarf, but it's so incredibly faint that ancient astronomers had absolutely no idea it existed. It wasn't discovered until 1915, using photographic techniques that could detect dim objects invisible to the human eye. Red dwarfs are cool compared to other stars. Their surface temperatures range from about 2,000 to 3,500 degrees Celsius, compared to about 5,500 degrees for the surface of our sun. This lower temperature is why they appear red to observers. Cooler objects glow with redder, longer wavelength light. But here's what makes red dwarfs truly special and important for our story. They live for an extraordinarily, almost incomprehensibly long time. Remember how a star's lifespan depends primarily on how fast it burns its fuel? Well, red dwarfs burn their fuel incredibly slowly. Their cores are cooler and less dense than the cores of larger stars. Nuclear fusion proceeds at a leisurely, unhurried pace. A red dwarf might take hundreds of billions of years to exhaust its hydrogen fuel completely. Some of the very smallest red dwarfs could potentially burn for 10 trillion years or even longer. Let me put that staggering number in some perspective. The universe is currently 13.8 billion years old. A small red dwarf could live for 10 trillion years. That's almost 1,000 times the current age of the entire universe. A red dwarf born today could still be shining steadily after a time span so vast that it makes the current age of the cosmos look like a single heartbeat, a fleeting instant in an almost eternal existence. There's another important reason why red dwarfs live so extraordinarily long. Most stars, including our sun, only burn the hydrogen located in their cores. The outer layers of the star never get hot enough for fusion to occur. So even though the sun contains enough hydrogen to theoretically fuel fusion for much longer, most of that hydrogen is trapped in the outer layers where it simply cannot be used. When the core hydrogen runs out, the star's main sequence life effectively ends, even though plenty of unused fuel remains tantalizingly out of reach. Red dwarfs are fundamentally different. They possess a special internal structure that allows them to access and burn a much larger fraction of their total hydrogen supply. We'll explore this remarkable mechanism in detail later, when we focus on the red dwarfs during their long reign over the dying universe. For now, what matters is the result. Red dwarfs can use their fuel far more efficiently than any other type of star. When a red dwarf finally exhausts its hydrogen after trillions of years, it won't swell into a red giant like our sun will. It simply doesn't have enough mass for such dramatic expansion. Instead, it will contract and briefly heat up, then slowly fade into a white dwarf, and eventually cool into a black dwarf over additional billions of years. But the key point is this: red dwarfs will outlast every other type of star in the universe. Every massive star that exists today will be completely dead within a few million years at most. Every sun-like star will be dead within a few billion years. But the red dwarfs will keep burning steadily for trillions upon trillions of years after everything else has gone permanently dark. Now, let's talk about what's actually happening in the universe right now. Because the story of the last star begins today, in our present moment. Stars are still forming throughout the cosmos. Every year in the Milky Way alone, new stars are born from collapsing gas clouds. The exact rate varies depending on conditions, but roughly speaking, our galaxy produces a few new stars per year, on average. Star formation is most active in regions where gas and dust are particularly abundant, like the spiral arms of our galaxy where material is compressed by density waves. But here's the important thing to understand. The rate of star formation has been declining steadily for billions of years. The universe was much more active in the distant past. About 10 to 11 billion years ago, star formation was at its absolute peak across the cosmos. Galaxies were forming stars at a rate perhaps 10 times higher than we observe today. Since that cosmic peak, the rate has been steadily and consistently dropping. Why is this happening? Because the raw material needed for star formation is gradually running out. The gas clouds that form stars are being slowly depleted throughout the universe. Some gas gets permanently locked up in long-lived stars and stellar remnants and never returns to the interstellar medium. Some gas is heated by intense stellar radiation and pushed completely out of galaxies altogether. Some falls inexorably into the supermassive black holes that lurk at the centers of most galaxies. The universe isn't running out of matter entirely. There's still plenty of matter out there in various forms, but it's becoming progressively harder to gather that matter into the dense clouds needed for star formation. The universe is expanding relentlessly, spreading matter ever thinner across growing volumes of space. Galaxies are aging, their gas supplies slowly dwindling with each passing epoch. Right now, we're well past the peak of cosmic star formation. The universe is no longer the blazing furnace of stellar creation it once was in its youth. It's entering a long, slow, gradual decline. New stars are still being born, but fewer are created each year. And most of the stars being born in the current epoch are red dwarfs, the smallest and longest-lived variety. This is profoundly important for our story, because the stars being born today, the red dwarfs coming into existence right now in stellar nurseries throughout the cosmos, these are the very stars that will still be shining in the unimaginably distant future. Now, one of these red dwarfs, burning quietly and unremarkably somewhere in the universe today, might be the direct ancestor of the last star that will ever shine. The universe is approximately 13.8 billion years old. In cosmic terms, it's actually quite young. Very young, in fact. The stelliferous era, the age of stars, is expected to last for about 100 trillion years in total. We've witnessed only the first tiny fraction of it so far. The universe has been producing stars for less than 1% of the total time it will ultimately produce them. We live in the cosmic morning, not the evening. But eventually, even this age of stars will come to an end. The gas will finally run out completely. The last stellar nurseries will go cold and dark. No new stars will ignite anywhere in the cosmos. And then, slowly but inevitably, the existing stars will die off one by one, leaving only the longest-lived survivors behind, the red dwarfs. For trillions upon trillions of years, these tiny, dim, unremarkable stars will carry the torch of light through an increasingly dark and empty universe. Galaxies will still exist as gravitational structures, but they'll be collections of stellar corpses, white dwarfs cooling toward absolute zero, neutron stars spinning down, and black holes slowly evaporating. These dead galaxies will be illuminated only by the faint, reddish glow of the surviving red dwarfs, scattered like dying embers in an infinite darkness. And then, eventually, even the red dwarfs will begin to die, one by one across spans of time too vast for human comprehension. They'll exhaust their fuel and fade away into cold, dark remnants. The light in the universe will grow dimmer and dimmer with each passing trillion years, until finally, somewhere in the cosmos, the last red dwarf will burn through the very last of its hydrogen fuel. That star, that final ember glowing alone in an otherwise lightless universe, is what we're searching for tonight. The last star to ever exist. The ultimate survivor in a universe that will have grown cold and dark and empty around it. But to truly understand what that final moment will be like, we need to journey forward in time, far forward, further than any human being has ever seriously imagined going. We need to see what happens to the universe over trillions and trillions of years. We need to watch the stars slowly die, one era at a time. Now we begin our journey into the future. And I have to warn you, the timescales we're about to discuss are genuinely difficult for the human mind to grasp. Our brains evolved to comprehend seasons and lifetimes, not eons and eternities. We're going to travel forward by billions of years, then trillions of years. We're going to watch the universe age and change in ways that completely dwarf anything in human experience. The numbers will become so large that they lose meaning. But try to hold on to them anyway, because what we're describing is real. This is actually what will happen. Let's start with something relatively familiar. The next billion years. 1 billion years from now, the sun will be about 11% brighter than it is today. This might seem strange at first. Shouldn't a star stay roughly the same brightness throughout its life? But stars gradually increase in luminosity as they age, because fusion reactions slowly produce more helium in the core over time. Helium is denser than hydrogen, so as helium accumulates, the core contracts slightly under its own weight. This contraction makes the core hotter, which speeds up fusion, which produces more energy. The sun has been getting brighter by about 10% every billion years since it first ignited. This increasing brightness has profound consequences for Earth. 1 billion years from now, the average temperature on Earth's surface will be significantly higher than it is today. The oceans may begin to evaporate into the atmosphere. The water cycle that sustains all life will break down. Complex life may no longer be possible on our planet's surface. Earth's days as a habitable world are numbered, and that number, while vast by human standards, is finite. Our planet has perhaps 1 billion years of habitability remaining. We live in the final quarter of Earth's time as a living world. But for the universe as a whole, 1 billion years is essentially nothing. A blink. The briefest of moments. The stars will continue to shine throughout the cosmos. Galaxies will continue to turn in their slow, majestic rotations. New stars will continue to form in nebulae scattered across the universe, though at a gradually declining rate from the cosmic peak that occurred billions of years ago. 5 billion years from now, things get considerably more interesting. The sun will have exhausted the hydrogen in its core and will begin its dramatic transformation into a red giant. It will swell enormously, expanding to perhaps 200 times its current diameter, large enough to possibly engulf the orbits of Mercury and Venus. Its outer layers will billow out into space like a slow-motion explosion frozen across millions of years. Earth will likely be scorched beyond recognition, its oceans long since boiled away, its atmosphere stripped, its surface possibly melted by the approaching stellar furnace. Whether Earth is actually swallowed or merely baked depends on complex interactions between the expanding sun and the planet's orbits, but either way, our world will cease to be anything we would recognize. Around the same time, give or take a few 100 million years, the Milky Way will collide with the Andromeda galaxy. I use the word collide, but that's somewhat misleading. It's more accurately described as a merger or a gravitational dance. The two galaxies will pass through each other, their individual stars mostly missing one another because stars are so incredibly far apart relative to their sizes. If you shrank the sun to the size of a grain of sand, the nearest star would be another grain of sand about 20 miles away. Galaxies are mostly empty space. Stars will not collide in any significant numbers, but the gravitational interaction will be dramatic nonetheless. The shapes of both galaxies will be completely disrupted. The elegant spiral arms of the Milky Way will be torn apart and stretched into vast streams of stars. Andromeda will suffer similar distortion. Stars will be flung in all directions by the chaotic gravitational field. The two galaxies will pass through each other, swing around, pass through again, and gradually settle over billions of years into a single large elliptical galaxy. Some astronomers have nicknamed this future merged galaxy Milkomeda. Others call it Milkdromeda. Whatever we name it, this merged galaxy will be our cosmic home for the rest of the universe's stellar history. 7 billion years from now, the sun will have completed its transformation. The outer layers will have drifted away from the core, forming a beautiful planetary nebula that will glow with fluorescent light for a few tens of thousands of years, before gradually fading into invisibility. The core will remain behind as a white dwarf, roughly the size of Earth, but containing about half the sun's original mass. It will be incredibly hot at first, perhaps 100,000 degrees at its surface, and will shine with an intense bluish-white light. But without fusion to sustain it, without any internal energy source to replenish what it radiates away, it will begin a long, slow, cooling process that will last for billions upon billions of years. Now, let's jump forward considerably. 20 billion years from now. The universe is now about 34 billion years old, approaching 3 times its current age. The expansion of space has continued relentlessly, driven by the mysterious force we call dark energy. Distant galaxies that were once visible in our telescopes have been carried beyond our cosmic horizon by this expansion. Their light can no longer reach us because space between us and them is expanding faster than light can cross it. The observable universe has grown darker, not because galaxies have disappeared or been destroyed, but because space has expanded so much that light from distant galaxies is stretched into invisibility, redshifted beyond detection. Star formation has declined significantly throughout the cosmos. The great star-forming nebulae are mostly exhausted, their gas either consumed by previous generations of stars or dispersed by stellar winds and supernova explosions. The Orion Nebula, if anything remains of it, is dark and cold and quiet. Most stars being born now are red dwarfs, the smallest and least demanding of fuel, because only the densest remaining pockets of gas can still collapse into stars. The sun's white dwarf remnant has cooled considerably over these 20 billion years. It no longer glows with visible light. It has become what astronomers call a black dwarf, a cold, dense ball of carbon and oxygen drifting invisibly through space. But other white dwarfs, Younger ones formed from stars that died more recently still glow faintly with residual heat. The galaxy contains trillions of these cooling stellar corpses, slowly fading toward darkness. 100 billion years from now, the universe is approaching a major transition point. It's now about 114 billion years old, more than 8 times its current age. Star formation has slowed to a mere trickle of what it once was. Most galaxies have either merged into giant elliptical galaxies through countless collisions and gravitational interactions, or have dispersed their stars entirely, flinging them into intergalactic space through close encounters. The expansion of space has accelerated continuously due to dark energy, stretching the universe at an ever-increasing rate. Here's something truly remarkable about this era that deserves careful consideration. If intelligent beings existed at this time and tried to study cosmology, tried to understand the universe they lived in, they would see something profoundly different from what we see today. They would see only their local group of gravitationally bound galaxies, perhaps just one giant elliptical galaxy if most mergers have completed. Everything else, every other galaxy in what we now call the observable universe, would have been carried beyond the cosmic horizon by expansion. They would be invisible, unreachable, as if they never existed. These future cosmologists would see no evidence of the Big Bang, the cosmic microwave background radiation, the afterglow of creation that we can detect today and that tells us so much about the universe's origins, would have been stretched to completely undetectable wavelengths by the expansion of space. The temperature of this radiation would have dropped so close to absolute zero that no instrument could measure it. They might conclude, reasonably based on their evidence, that their galaxy is all that exists, floating alone in an infinite and eternal void. The universe would effectively hide its own history from these future observers. The evidence we have today, the distant galaxies we photograph, the cosmic background radiation we map, the patterns of large-scale structure that tell us the story of the Big Bang and cosmic evolution, all of that would be invisible to them. The universe would appear static and eternal to their instruments, not expanding and evolving as we know it to be. These future beings would have no way to know the truth about the cosmos unless they somehow inherited records from earlier civilizations. The universe itself would lie to them through omission. This cosmological blindness would extend to every major discovery we take for granted. The expansion of the universe, first observed by Edwin Hubble in the 1920s, would be undetectable because there would be no distant galaxies to measure receding from the observer. The age of the universe, which we calculate by running the expansion backward to a single point, would be incalculable. The abundance of hydrogen and helium, which matches predictions from Big Bang nucleosynthesis and provides powerful evidence for the hot, dense early universe, would seem like just the way things are rather than a clue to cosmic origins. These future astronomers might develop physics and chemistry. They might understand nuclear fusion and stellar evolution. They might even deduce that their galaxy is slowly dying, that the red dwarfs are gradually fading, that darkness is coming. But they would have no way to know that their universe was ever different. No way to know that trillions of galaxies once filled the observable cosmos. No way to know that their lonely galaxy was once part of a vast cosmic web of structure stretching across billions of light years. We are living in a privileged time for cosmology. The evidence of the universe's origin is visible to us. The story of creation is written in the sky for anyone with the right instruments to read. In 100 billion years, that story will be erased. The universe will have hidden its own autobiography. This raises a haunting question. What evidence might already be lost? What cosmic truths were once visible, but have since faded beyond detection? Are there aspects of the universe's earliest moments that we will never know because the evidence has already been stretched into invisibility? We assume we can reconstruct cosmic history from what we see today, but perhaps we too are missing chapters that were only readable in earlier epochs. The universe reveals its secrets grudgingly, and only for limited windows of time. We happen to live in a window when much can still be learned. That window will not stay open forever. 1 trillion years from now. We've now jumped forward by an order of magnitude. The universe is 1 trillion years old, almost 100 times its current age. Try to hold that number in your mind. 1 trillion years. 1,000,000,000 years. 1,000 billion years. Star formation has essentially stopped everywhere in the universe. The gas has been exhausted. The last stellar nurseries went cold and dark billions of years ago. No new stars are being born anywhere in the cosmos. The era of stellar creation, which began about 200 million years after the Big Bang, has finally ended after a run of roughly 100 trillion years. The only stars still shining are the longest-lived red dwarfs, and even these are beginning to die off in significant numbers. Red dwarfs born early in the universe's history, during the peak of star formation 10 or 11 billion years after the Big Bang, have already exhausted their fuel. The first generation of red dwarfs is completely gone. The second generation is fading rapidly. Only the youngest red dwarfs, those formed relatively late in the star-forming era, still burn with nuclear fusion. Galaxies have changed dramatically from the structures we know today. The great spiral structures with their elegant arms and dense cores are completely gone. Most galaxies have merged into giant elliptical blobs or have dispersed entirely due to gravitational interactions over trillions of years. Stars that were flung out during galactic mergers wander alone through the vast emptiness of intergalactic space. Orphans in the void, separated from their siblings by distances too vast to ever cross. The stellar population has shifted profoundly. In the present-day universe, you have a wonderful mix of stellar types. Massive blue giants burning brief and brilliant, medium-sized yellow stars like our sun living for billions of years, and small red dwarfs destined to persist for trillions. 1 trillion years from now, only red dwarfs remain as active, fusion-powered stars. The massive stars all died after mere millions of years. The sun-like stars all died after billions. Only the patient, frugal red dwarfs persist into this distant era. The universe is dimmer now. Much, much dimmer than today. Each red dwarf produces only a tiny fraction of the light our sun produces. Some as little as 1/10,000th as much. Where once there were diverse stellar populations lighting up galaxies with blue and white and yellow and orange and red light, now there are only these faint red embers scattered through the immense darkness of space, but there's still light. The red dwarfs still shine, planets might still orbit some of them, warmed by their faint reddish glow. If life exists on those planets, it exists in a universe vastly different from ours. A universe where distant galaxies are completely invisible, where the evidence of cosmic origins has been erased by expansion. What would such beings think of the cosmos? What stories would they tell about their place in existence? 10 trillion years from now. This is approximately when the last red dwarfs will begin to die in large numbers. Let me be more precise about this timeline, because the details matter for understanding how the end will come. Red dwarf lifespans depend critically on their mass. The smallest red dwarfs, those with about 8% of the Sun's mass, barely massive enough to sustain fusion at all, can theoretically burn for about 10 trillion years. Larger red dwarfs, with perhaps 40 or 50% of the Sun's mass, will die considerably sooner, perhaps after 1 or 2 trillion years of steady burning. So around this time, 10 trillion years from now, even the longest-lived red dwarfs are approaching the end of their fuel supply. The ones born early in cosmic history are long dead and cold. The ones born later are dying now, one by one across the universe. Only the very last generation, the youngest red dwarfs formed just before star formation, ceased entirely, still burn with the light of nuclear fusion. The universe has grown profoundly dim by this point. Imagine standing on a planet orbiting one of these final red dwarfs. You look up at the night sky and see almost nothing. Your star provides a dim, reddish light, barely enough to see by, casting everything in shades of deep crimson and shadow. Other stars? There are so few remaining that you might see only 1 or 2 faint points of reddish light in the entire sky, or perhaps none at all, depending on where you happen to be located. The familiar patterns, the constellations that meant so much to countless civilizations, are gone forever. The galaxies, if you could somehow see them, would be graveyards. Vast collections of stellar corpses drifting through space. White dwarfs that have cooled into invisible black dwarfs. Neutron stars that have stopped pulsing. Black holes that swallow any matter, unfortunate enough to approach. Nothing shines except the last red dwarfs, scattered thinly through the darkness like the final embers of a dying fire. The universe has become a cosmic cemetery, and these few remaining stars are the last candles still burning. 20 trillion years from now. We're deep in the twilight of the stellar era now. The last significant population of red dwarfs is gone. Only stragglers remain. The occasional red dwarf that formed unusually late in the star-forming era, or that was somehow exceptional in its mass or composition. These final stars are extraordinarily rare. Perhaps 1 in a million of the original stellar population still shines. The universe is not completely dark yet. Occasionally, dim events briefly light up small patches of the void. When 2 white dwarfs collide, spiraling together over billions of years due to gravitational radiation, the merger can temporarily produce light and heat. When matter falls into a black hole, it heats up to incredible temperatures and glows brilliantly before vanishing forever beyond the event horizon. When 2 neutron stars merge, they produce a kilonova, a brilliant flash that briefly illuminates the surrounding space with more light than 1 billion suns. But these events are fleeting. They last for days or weeks or months, not for billions of years like stars do. They are fireworks, not campfires. The steady, reliable glow of stellar fusion is almost gone from the universe. Only a handful of red dwarfs still burn, scattered incredibly far apart across what remains of the galactic structures that once organized matter into beautiful spirals and ellipses. 50 trillion years from now. By this point, we're approaching the definitive end of the stelliferous era. The age of stars, which defined the universe for so long, is almost over. The red dwarfs are essentially extinct as a population. Perhaps a few hundred remain in what was once the Milky Way galaxy, perhaps a few hundred more in each of the other former galaxies scattered across the observable universe. Across the entire cosmos, perhaps a few million red dwarfs still shine with the light of nuclear fusion. That might sound like a substantial number, but remember the scale we're dealing with. The Milky Way alone once contained hundreds of billions of stars. The observable universe once contained 2 trillion galaxies. Now, across all that incomprehensible vastness, only a few million points of light remain. It's like a city that once blazed with 10 billion lights, now reduced to a handful of candles. These final red dwarfs are the smallest and coolest of their kind. They produce barely enough energy to technically qualify as stars. Some are so faint that they produce less total light than the full moon reflects from our sun. They're not much to look at by any standard, but they're all that remains of the stellar era. The last bearers of a torch that has burned for 100 trillion years. The universe has been growing dark for so long now that the very concept of brightness has fundamentally changed. If intelligent beings existed at this time, their eyes and their instruments would have evolved for darkness. Our sun would seem blindingly, painfully, impossibly bright to them, an explosion of light beyond their comprehension. Their dim red dwarfs would seem comfortable and normal and sufficient. Darkness would be their default state, their baseline, their home. 100 trillion years from now, this is traditionally considered the end of the stelliferous era, the age of stars, the time when the last fires finally go out. Some models suggest that by this point, essentially all normal red dwarfs have died. The universe no longer produces significant light through stellar fusion. The stars, which have burned since the universe was young, are finally gone. Darkness has won. But let me be careful here, because the reality is messier than that clean number suggests. Stellar evolution is fundamentally probabilistic. There will be outliers. Statistical anomalies, red dwarfs that formed unusually late in the final gasp of star formation. Red dwarfs that are unusually small, right at the minimum mass for fusion, and hence unusually long-lived. Red dwarfs that somehow received fresh hydrogen fuel from collisions with other objects, or accretion from stray gas clouds. There will be stragglers who defy the averages. So, while 100 trillion years marks the approximate end of the stellar era for practical purposes, there will still be a few stars after that arbitrary marker. A few last holdouts, clinging to existence in a universe that has largely gone dark around them. Rare, precious, and utterly alone. And among those final holdouts will be the last star. The very last star to ever shine in the history of the universe. We don't know exactly when it will finally die. It depends on factors we cannot possibly predict. Exactly how small the smallest viable red dwarfs can be, exactly when the last generation of stars formed before star formation ceased, exactly what rare and unlikely events might briefly reignite fusion in stellar remnants that would otherwise have died. But somewhere between 100 trillion and 1 quadrillion years from now, the last star will exhaust its fuel. The last nuclear fusion reaction will occur in its core. The last photons generated by that fusion will radiate outward into the void. The last light will fade. And then, for the first time since the universe was about 200 million years old, there will be no stars anywhere. The darkness that follows will not be temporary. It will not be a pause before a new dawn. There will be no new stellar era waiting to begin. The raw materials for stars are exhausted. The conditions for star formation are gone forever. The darkness that descends after the last star dies will last for the remaining eternity of the universe, however long that might be. We have witnessed in our imagination the end of light itself, the stelliferous era, spanning from the first stars to the last, will have lasted perhaps 100 trillion years, or slightly more. We currently live in the first tiny fraction of that era, in the bright morning of a cosmic day that will eventually fade into an endless night. But to understand the final moments of stellar history, we need to look more closely at the red dwarfs themselves. These patient survivors who will carry the torch of starlight longer than any other objects in the cosmos. Their unique physics, their remarkable efficiency, and their extraordinary longevity make them the protagonists of the universe's longest chapter. Understanding them is essential to understanding how it all ends. We've traveled forward in time, watching the universe age and transform in ways almost impossible to comprehend. We've seen star formation decline from its ancient peak, galaxies merge and fade into gravitational ghosts of their former glory, and most stars die off one by one across the eons. Now, let's spend some time with the true heroes of cosmic longevity, the red dwarfs, the patient ones, the survivors. Red dwarfs deserve our careful attention because they dominate the final chapters of the universe's story. For trillions upon trillions of years, they'll be the only stars shining anywhere in the cosmos. Understanding them means understanding what the universe will be like for most of its remaining stellar existence. They are not the brightest characters in cosmic history, not the most dramatic, not the most visually spectacular, but they are the ones who will still be standing when everyone else has fallen. In the story of the universe, red dwarfs are the quiet heroes who outlast all the louder, flashier protagonists. Let me tell you more about what makes red dwarfs so remarkably special. A red dwarf is a star with a mass between about 8% and 50% of our sun's mass. This range might seem arbitrary, but it's defined by fundamental physics. Below 8% of the sun's mass, you don't have enough gravitational pressure and core temperature to sustain hydrogen fusion. The object might glow for a while from the heat of its formation, but it will never achieve the self-sustaining nuclear reactions that define a true star. Above 50% of the sun's mass, you start getting into the territory of K-type and G-type stars, larger and hotter objects that burn their fuel more quickly. Red dwarfs occupy this narrow but crucial band, small enough to be dim and cool, but massive enough to be true stars with fusion burning in their cores. The smallest red dwarfs exist on a knife's edge between stellar existence and failed stardom. Proxima Centauri, the closest star to our sun at just over 4 light-years away, has a mass of about 12% of the sun's mass. That's just barely above the minimum threshold for sustained fusion. If Proxima Centauri was slightly less massive, perhaps 10% less, it would be a brown dwarf instead. A failed star that cannot sustain the fusion reactions that define stellar existence. It would glow dimly for a time from residual heat, and then fade into cold darkness. The physics of red dwarfs is genuinely fascinating, and understanding it helps explain why these modest stars will outlast all others. Their cores are cooler and less dense than the cores of larger stars. In our sun, the core temperature reaches about 15 million degrees Celsius, hot enough to drive fusion at a rate that will consume the core's hydrogen in about 10 billion years. In a typical red dwarf, the core temperature might be only about 4 million degrees Celsius. This lower temperature has profound consequences for the star's behavior and lifespan. Nuclear fusion requires atomic nuclei to overcome their natural electrical repulsion. Protons are positively charged, and positive charges repel each other. For two protons to fuse, they must be moving fast, enough to overcome this repulsion and get close enough for the strong nuclear force to take over and bind them together. Temperature is essentially a measure of how fast particles are moving. At lower temperatures, fewer nuclei have enough energy to overcome the electrical barrier. Fusion reactions happen less frequently. This slow fusion rate is why red dwarfs are so incredibly dim. Proxima Centauri produces less than 2/1000th of the total energy our Sun produces. Most of that energy emerges as infrared radiation rather than visible light, making red dwarfs even dimmer to human eyes than their total energy output would suggest. If you replaced our Sun with Proxima Centauri, keeping everything else the same, Earth would freeze solid almost immediately. The oceans would become ice, the atmosphere would begin to snow out. Red dwarfs provide only a fraction of the warmth and light that we take for granted from our own star, but this slow fusion rate is also precisely why red dwarfs live so extraordinarily long. They're burning their fuel at an almost miserly pace, conserving their hydrogen over timescales that dwarf the current age of the universe. Our Sun will exhaust the hydrogen in its core in about 5 billion more years. Proxima Centauri, with its slower fusion rate and its ability to access more of its total fuel supply, could take 4 trillion years or more to exhaust its hydrogen. That's almost 300 times the current age of the universe. Now let me explain in detail the mechanism that makes this extreme longevity possible, because it's one of the most elegant features of stellar physics. In our Sun, energy generated in the core travels outward through what's called a radiative zone. In this region, energy moves primarily through radiation. Photons are emitted by hot plasma, travel a short distance, are absorbed by other plasma, which then emits new photons, which travel another short distance, and so on. The photons bounce around randomly, slowly, making their way from the core toward the outer layers through countless absorption and emission events. It can take a photon somewhere between 100,000 and 200,000 years to complete this journey from the core to the surface. The process is extraordinarily slow, a random walk through incredibly dense material. Above the radiative zone in our Sun is a convective zone, where energy is transported by rising and falling currents of plasma. Hot material rises from the bottom of this zone, cools as it reaches the surface and radiates energy into space, then sinks back down to be reheated. This convection is similar to what happens in a pot of water on a stove. But crucially, in our Sun, this convective zone doesn't extend all the way down to the core. The radiative zone separates the convective zone from the fusion-producing core. This separation has profound consequences for how efficiently the Sun can use its fuel. In red dwarfs, the physics works entirely differently. There is no radiative zone at all. The entire star, from the core to the surface, is convective. Hot material rises from the very center of the star, travels all the way to the surface, cools as it radiates energy into space, and then sinks all the way back down to the core. The whole star circulates continuously, like water in a pot brought to a rolling boil on a stove. This total circulation mixes the star thoroughly and constantly. Fresh hydrogen from the outer layers is continuously being drawn into the core, replenishing the fuel supply for fusion. Meanwhile, Helium produced by fusion reactions is carried outward and distributed throughout the entire star rather than accumulating in the core. This is completely different from our Sun, where helium steadily accumulates in the core, while the hydrogen in the outer layers sits unused, inaccessible to the fusion reactions happening deep inside. Because of this convection, red dwarfs can burn a much larger fraction of their total hydrogen over their lifetimes. Our Sun will only fuse about 10% of its total hydrogen before leaving the main sequence and beginning its transformation into a red giant. The other 90% of the Sun's hydrogen will never participate in fusion at all. It will either be expelled into space when the Sun sheds its outer layers, or it will remain trapped in the white dwarf remnant, never having contributed to the star's energy production. A red dwarf, by contrast, can fuse most of its hydrogen, perhaps 70% or more of its total supply. The convection continuously brings fresh fuel to the core and removes the helium ash, allowing the fusion reactions to continue far longer than they would otherwise. It's like the difference between a car that can only access the fuel in a small reserve tank versus a car that can efficiently use almost everything in its entire fuel system. Red dwarfs are remarkably efficient users of their nuclear fuel. This efficient fuel usage, combined with the inherently slow fusion rate due to lower core temperatures, is why red dwarfs live for trillions of years. They burn slowly and they burn thoroughly, extracting energy from their hydrogen supplies with a patience that puts all other stars to shame. There's another interesting and somewhat counterintuitive aspect of red dwarf behavior. As a red dwarf ages, it actually gets hotter and brighter, not dimmer as you might expect. This seems strange at first consideration. Shouldn't a star that's gradually using up its fuel get fainter as it approaches the end of its life? But remember, the fuel isn't running out quickly. The star has trillions of years worth of hydrogen. What's happening is more subtle and involves the changing composition of the star over time. As the red dwarf fuses hydrogen into helium over billions and trillions of years, the helium gradually accumulates throughout the star, distributed by the convection we discussed. Helium is denser than hydrogen. As the helium content of the star increases, the star as a whole becomes denser and more compact. This increased density causes the core to compress slightly and heat up. The higher core temperature increases the fusion rate, which produces more energy, which makes the star brighter and shifts its color slightly toward the blue end of the spectrum. A red dwarf that has been burning for trillions of years will actually be noticeably brighter than it was at birth. Not dramatically brighter, perhaps by a factor of 2 or 3, but significantly so. The color will shift as well, becoming less red and more orange or even yellowish as the surface temperature rises. This means that as the universe ages and red dwarfs come to dominate the stellar population, the surviving red dwarfs will actually be at their brightest and most energetic. What would life be like in the era when red dwarfs dominate the cosmos? Could intelligent beings exist, building civilizations around these dim, long-lived stars? Theoretically, yes. Red dwarfs can have planets, and we've discovered many such planetary systems in our own time. Proxima Centauri has at least 2 known planets orbiting it. One of them, designated Proxima Centauri b, orbits within the habitable zone, the region around a star where temperatures might allow liquid water to exist on a planet's surface. The discovery of this planet generated enormous excitement, precisely because it demonstrated that Earth-sized worlds can exist in the habitable zones of red dwarfs. But life around red dwarfs would face unique challenges that life on Earth has never encountered. Because red dwarfs are so dim, the habitable zone is very close to the star, much closer than Earth's comfortable distance from the Sun. Proxima Centauri b orbits at only about 5% of Earth's distance from our Sun. At this close range, the planet is almost certainly tidally locked, meaning one side always faces the star while the other side always faces away into space. Imagine a world where the sun never sets on one hemisphere and never rises on the other. The day side would be eternally illuminated by dim, reddish light, always afternoon, always the same temperature, never experiencing dawn or dusk or night. The night side would be eternally dark, always midnight, always cold, never warmed by direct starlight. Between them might exist a twilight zone, a band around the planet where the star perpetually sits on the horizon, casting long shadows that never move. Life might concentrate in this twilight region, or it might adapt to the extreme conditions of permanent day or permanent night. Red dwarfs are also prone to stellar flares, sudden and violent releases of energy that can be much more powerful relative to the star's normal output than the solar flares our sun produces. A large red dwarf flare might temporarily multiply the star's brightness by several times, bathing nearby planets in intense ultraviolet and X-ray radiation. These flares could blast nearby planets with enough radiation to strip away atmospheres over time and sterilize any life on exposed surfaces. This is especially concerning for planets in the habitable zone, which are so close to their stars that they receive the full force of any flare activity. But these challenges might not be insurmountable. Life is remarkably adaptable, and evolution has billions of years to find solutions to any problem. Thick atmospheres can provide shielding against radiation. Strong magnetic fields can deflect charged particles. Oceans can absorb heat and distribute it around a planet, moderating temperature extremes between day and night sides. Life might evolve to live underground or in deep water, protected from surface radiation. Organisms might develop biological radiation resistance far beyond anything found on Earth. And over trillions of years, there would be extraordinary amounts of time for evolution to explore every possibility. Life on Earth has existed for less than 4 billion years. A red dwarf could provide stable conditions for hundreds of times longer. What might evolution achieve with such vast stretches of time to work with? The beings that might exist in the red dwarf era would experience a universe entirely unlike the one we know. They would have no knowledge of brilliant blue stars or warm yellow suns like ours. Their entire experience of stellar light would be the dim, reddish glow of red dwarfs. This would seem entirely normal to them. They might find the concept of a star as bright as our sun to be absurd, an impossibility, something from mythology or fever dreams. If they somehow learned of our era, they might not believe such brightness was ever possible. Their night skies would be sparse compared to ours. In our sky, on a clear dark night, we can see thousands of stars with the naked eye. The Milky Way stretches across the heavens as a river of light composed of countless distant suns. The red dwarf era, far fewer stars would remain visible. The distances between surviving red dwarfs would be enormous. A civilization might look up and see only a handful of faint points of light, or perhaps nothing at all beyond their own sun. Communication between civilizations, if multiple civilizations somehow existed in this era, would be extraordinarily difficult. The distances would be too great. Radio signals would take thousands or millions of years to cross the gulfs between stars. The signals would be so faint after such journeys that detecting them would require technology beyond anything we can currently imagine. Each civilization would be effectively alone, isolated in the darkness, unable to know whether anyone else existed anywhere in the universe. But there would be one extraordinary compensation for all this isolation and darkness: time. If a civilization arose around a red dwarf in this era, it would have trillions of years to develop. Our sun will only remain stable enough for Earth to be habitable for another billion years or so, and will only remain on the main sequence for another 5 billion. A red dwarf civilization could have hundreds or thousands of times that long. What might a civilization achieve with 1 trillion years to grow and develop? We've had written language for about 5,000 years. Science as we know it is only a few centuries old. In 1 trillion years, a civilization could develop technologies we cannot even conceptualize. They could undertake projects spanning millions of years. They could think thoughts that would take generations to complete. Time, that most precious of all resources, would be abundant beyond measure. Consider what such a civilization might contemplate and attempt. They might construct megastructures that dwarf anything we can imagine, building across time scales of millions of years without urgency. They might develop forms of thought and consciousness that we would not recognize as intelligence. Slow and distributed processes that unfold across millennia, the way our thoughts unfold across seconds. They might cultivate patience as their highest virtue, measuring progress in geological epochs rather than human lifetimes. They might also face a unique existential perspective. They would know, if they understood stellar physics, that their star would eventually die. But that death would be so far in the future, trillions of years away, that it might seem almost theoretical. Imagine knowing your sun would last 1,000 times longer than the current age of our entire universe. Would death still feel real? Would urgency have any meaning? Would they even develop concepts like hurry or deadline or running out of time? Or perhaps the opposite would occur. Perhaps knowing that even trillions of years must eventually end would give them a profound appreciation for finitude, that we, with our brief lives and brief stellar era, can only dimly grasp. Perhaps they would understand mortality in ways that we, who live and die in the blink of a cosmic eye, never truly can. A creature that lives for a day cannot truly understand what it means to age. Perhaps only a civilization that watches the stars themselves grow old can truly comprehend what ending means. They might develop philosophies of time and existence that we cannot imagine. They might find meaning in the slow unfolding of cosmic processes that we would find unbearably tedious. Or they might find the universe unspeakably lonely, knowing that no other civilizations are likely to exist within any reachable distance, knowing that they are almost certainly alone in the darkness. What stories would they tell? What would their religions contemplate? What would they dream about? We cannot know. But their existence, if it occurs, will represent the longest continuous thread of complexity and consciousness in cosmic history. Eventually, of course, even the most patient red dwarfs exhaust their fuel. When a red dwarf has converted most of its hydrogen to helium, fusion becomes increasingly difficult to sustain. The core temperature, despite rising over the star's lifetime, never reaches the threshold needed to fuse helium into heavier elements as larger stars do. Without a new source of fusion energy, the star has no way to fight gravity's inward pull. The star contracts and heats up, briefly becoming what theorists call a blue dwarf as it shrinks and its surface temperature rises. This blue dwarf phase is a final flourish, a last brightening before the end. Eventually, without fusion to sustain it, the star contracts one final time and becomes a white dwarf, a dense remnant slowly cooling toward absolute zero. These red dwarf white dwarfs are different from white dwarfs produced by sun-like stars. When our sun becomes a white dwarf, it will be made mostly of carbon and oxygen, the products of helium fusion during the red giant phase. But red dwarfs never get hot enough to fuse helium. Their white dwarfs will be made mostly of helium instead, the accumulated ash of hydrogen fusion that was never processed further. These helium white dwarfs will be small, even by white dwarf standards. They'll have masses perhaps a tenth to a quarter of the sun's mass, reflecting the small masses of the red dwarfs that created them. And they'll begin the long, slow process of cooling that all white dwarfs undergo, radiating away their residual heat into the ever-expanding void of space. As we approach the end of the red dwarf era, the remaining stars become increasingly precious. Each one is a tiny island of warmth and light, floating in an infinite ocean of cold darkness. Galaxies, to the extent that they still exist as coherent gravitational structures, are vast graveyards of stellar corpses, punctuated by occasional faint red glows. The universe has been dark for so long that light itself has become rare, precious, something to be treasured. The last generations of red dwarfs are the smallest and most frugal of all stars that have ever existed. They were born from the final wisps of gas, just before star formation ceased entirely across the cosmos. They've been burning slowly and steadily for trillions of years, carefully conserving their fuel, extracting every possible erg of energy from their hydrogen supply. They represent the ultimate in stellar efficiency, the most patient objects the universe has ever produced. But even the most efficient stars eventually run out of fuel. Even patience has limits when measured against eternity. One by one, the last red dwarfs exhaust their hydrogen. One by one, they contract into white dwarfs and begin the long cooling process toward absolute darkness. The lights in the universe go out, slowly but inexorably, like candles being extinguished one at a time in an endless cathedral. And finally, after roughly 100 trillion years of stellar history, we reach the end of the age of stars. One star remains. Just one. The last star. It shines alone in a universe that has grown dark around it. It is the final ember of a fire that once filled the cosmos with light. It is the last representative of an era that began when the universe was young and that has now stretched across almost inconceivable spans of time. This star, whatever its name or location, will have the distinction of being the last. When it finally exhausts its fuel and fades into darkness, the stelliferous era will truly end. The universe will enter a new phase. A phase without stars, without fusion, without the steady light that has characterized existence since the first stars ignited hundreds of millions of years after the Big Bang. That final star deserves our contemplation, our respect, and perhaps our mourning. It represents the end of something profound, the conclusion of the era that made life possible, the final page of the longest chapter in cosmic history. When it fades, the lights go out forever. We've arrived at the moment this entire journey has been leading toward. The end of the stelliferous era. The death of the last star. Everything we've discussed. All those trillions of years of cosmic evolution, all those generations of stars living and dying, has been building to this single, quiet moment when the last nuclear fire finally goes out. Let me paint a picture of what this might look like. The last star is a red dwarf. It has to be. Nothing else could possibly have survived this long. Every massive star died within millions of years of its birth. Every sun-like star died within billions. Only the red dwarfs had the patience, the efficiency, the sheer stubborn longevity to persist into this late era. And among the red dwarves, only the smallest and most frugal could make it this far. The last star is one of the smallest stars possible, with a mass just barely above the minimum threshold for sustained hydrogen fusion. Perhaps 8 or 9% of our sun's mass. Any smaller and it would have been a brown dwarf, never achieving true stellar status at all. This star exists right at the boundary between stardom and failure, and that marginal existence is precisely what allowed it to outlast everything else. It formed late in the star-forming era, perhaps 90 or 100 trillion years ago, in the final gasp of cosmic star formation. It was born from one of the last clouds of gas to successfully collapse into a star, a wisp of hydrogen and helium that somehow gathered enough mass to ignite fusion in its core. All around it, other stars formed at the same time, a final generation of red dwarfs emerging from the last stellar nurseries. But those companion stars have all died now. They were slightly larger, burned their fuel slightly faster, and exhausted their hydrogen supplies millions or billions of years before this last survivor. The last star is old, inconceivably, incomprehensibly old. It has been burning steadily for nearly 100 trillion years. During that unimaginable span of time, it has witnessed more cosmic history than any mind could comprehend. It was already shining when the first red dwarfs began to die, when stars that had burned for trillions of years finally exhausted their fuel. It was shining when the last sun-like star, some ancient yellow dwarf that had somehow persisted longer than expected, finally faded into a white dwarf remnant. It was shining as the universe grew darker and darker around it, as the other red dwarfs winked out one by one across the cosmos, each death leaving the universe slightly emptier than before. And now, it's alone. Utterly, completely, cosmically alone. The last point of fusion-powered light in a universe that has grown dark. What does the universe look like from the vicinity of the last star? If you could somehow be there, floating in space near this final ember, you would experience a darkness unlike anything possible in our current universe. The star itself provides a dim, reddish glow, barely enough illumination to read by if you held a book close to your face. But beyond that modest sphere of light, beyond the small region where the star's radiance makes any difference at all, there is only darkness. Absolute, complete, and perfect darkness. There are no other stars visible anywhere in the sky. Not a single one. The nearest stellar remnants, white dwarfs that cooled into black dwarfs countless eons ago, are completely invisible because they emit no light whatsoever. They're out there, drifting through space in numbers beyond counting, but they're as dark as the void around them. The nearest black holes are invisible because they're black holes, regions of space where light cannot escape. The nearest neutron stars might emit faint trickles of radiation, but they're so far away and so dim after trillions of years of cooling that they can't be detected by any reasonable means. If you looked up at the sky from a planet orbiting the last star, you would see black, complete, total perfect, absolute black. Not the kind of darkness you experience on a moonless night on Earth, where there are still stars scattered across the heavens, and perhaps the soft glow of the Milky Way stretching from horizon to horizon. This is the utter absence of all light. An emptiness so complete, so total that your eyes would have nothing to adjust to. You could wait for hours, for days, for years, and your night vision would never improve because there is simply no light to see. The black of the night sky would be indistinguishable from having your eyes closed. The only difference between looking up and looking down, between looking outward and closing your eyes, would be the faint reddish glow of the last star if it happened to be above your horizon at that moment. Otherwise, perfect darkness in every direction, forever. The last star probably has planets, worlds that have circled this dim ember for trillions of years, held in their orbits by gravity's patient grip. These planets would be old beyond imagination, their surfaces shaped by processes we can barely conceive operating over timescales we cannot truly comprehend. If life ever existed on these planets, if intelligent beings ever walked their surfaces and looked up at their dim red sun, they would have had an unimaginably long history. Trillions of years of potential civilization, of evolution, of culture and thought and existence. What might beings accomplish with such vast stretches of time? What thoughts might they think? What meanings might they find in a universe grown dark around them? But by now, even they might be gone. 1 trillion years is such a long time that the word long loses all meaning. Civilizations rise and fall on timescales of thousands of years. Species evolve and go extinct on timescales of millions. Planets change, their surfaces transformed by geological processes, their atmospheres altered by chemistry and physics, on timescales of billions. After trillions of years, whatever existed around this star has probably transformed beyond all recognition or vanished entirely. The planets might remain, but any life they once harbored is likely long gone. The last star burns on, unaware that it is the last. Stars don't know they're stars. They don't feel or think or understand. They have no consciousness, no awareness, no sense of their own existence or importance. They simply burn following the laws of physics with perfect fidelity, converting hydrogen to helium and releasing energy according to equations that have governed nuclear reactions since the universe began. The last star does this, just as the first stars did, over 13 billion years earlier in cosmic history. The process is identical, only the context has changed beyond all recognition. Inside the core of the last star, the hydrogen supply is nearly exhausted. For trillions of years, convection has mixed fresh hydrogen into the core, bringing fuel from the outer layers to sustain the nuclear fires burning at the center. This convection has been the star's salvation, the mechanism that allowed it to burn so much longer than it otherwise could have. But now, almost all the hydrogen throughout the entire star has been converted to helium. The fuel that sustained the star for 100 trillion years is finally running out. As the hydrogen becomes scarcer, fusion becomes increasingly difficult to sustain. The core must work harder to maintain the reaction rate that has held gravity at bay for so long. The energy output begins to decline. The delicate balance between gravity pulling inward and fusion pushing outward starts to shift. Gravity begins to win. The star begins to contract under its own weight, no longer fully supported by the outward pressure of fusion energy. This contraction is slow at first, almost imperceptible, but it accelerates as less and less fusion energy is available to resist it. And as the star contracts, something interesting happens. The Compression heats the stellar material, temporarily increasing the core temperature. The star transitions into what theorists call a blue dwarf phase, where the dying red dwarf briefly becomes hotter and bluer as it shrinks. This blue dwarf phase is short compared to the star's previous life, perhaps only a few billion years, a mere eye blink compared to the 100 trillion years of steady red dwarf existence. During this time, the star actually becomes brighter, even as it dies. Its surface temperature rises as the star compresses, shifting its color from deep red through orange and yellow toward blue-white. It's like a candle flaring up in one final burst of brightness just before it gutters and goes out. But the flare cannot last. Eventually, there's simply no hydrogen left to fuse. The convection that served the star so well for so long has done its job too thoroughly, bringing every last atom of hydrogen fuel into the core to be burned. Now there's nothing left. The core temperature drops below the threshold needed to sustain fusion reactions. The nuclear fire that has burned for 100 trillion years flickers and dies. When fusion ends, the star's fate is sealed. There's no longer any outward pressure to resist gravity's eternal inward pull. The star contracts one final time, collapsing until the electrons in its core become degenerate, meaning they're packed as tightly as the laws of quantum mechanics allow. No force can compress them further. The star reaches its final state, a white dwarf. But this white dwarf is different from most white dwarfs that formed earlier in cosmic history. It's made primarily of helium, not the carbon and oxygen that compose white dwarfs created from sun-like stars. This is because the last star never got hot enough to fuse helium into heavier elements. Its core never reached the temperatures required for helium burning. The helium that accumulated over trillions of years of hydrogen fusion simply sits there, compressed but unreacted, the ash of a fire that burned longer than any other. This helium white dwarf is also very small by white dwarf standards. It has perhaps only about 1/10 the mass of our Sun, reflecting the tiny mass of the red dwarf that created it. It's a small, dense ball of degenerate matter, the final compressed remnant of the last star. The white dwarf is hot at first, perhaps 20,000 degrees Celsius at its surface, glowing with an intense bluish-white light. For a brief time, astronomically speaking, it's actually brighter and more visually impressive than the red dwarf it came from. But without fusion to sustain it, without any internal source of energy to replenish what it radiates away, this brightness cannot last. The white dwarf has no source of energy except the heat stored in its compressed matter. That heat will slowly, inexorably radiate away into the cold void of space. The white dwarf begins to cool. 20,000 degrees becomes 15,000. 15,000 becomes 10,000. The color shifts from blue-white through white to yellow, like an ember cooling in a dead fire. 10,000 degrees becomes 5,000. The white dwarf now glows with a yellowish-orange light, similar to our Sun but far dimmer. 5,000 becomes 3,000. The light shifts to deep orange, then to red. 3,000 becomes 1,000. The white dwarf now emits primarily infrared radiation, invisible to human eyes, detectable only as a faint warmth against the cosmic background. As it cools further, it becomes harder and harder to detect. Its radiation shifts further into the infrared, then into microwaves, then into radio waves. 1,000 degrees becomes 500. 500 becomes 100. 100 becomes 10. The white dwarf is now barely warmer than the cosmic microwave background radiation. the faint afterglow of the Big Bang that fills all of space with a temperature of about 2.7 degrees above absolute zero. After perhaps 100 billion more years of cooling, the white dwarf has reached thermal equilibrium with its environment. It no longer emits any significant radiation. Its temperature has dropped to within a fraction of a degree of absolute zero. It has become what astronomers call a black dwarf, a cold, dark, dead ball of degenerate matter drifting invisibly through the void. And with that transition, the stelliferous era truly ends. The last star has died. Its light has faded. For the first time since the universe was approximately 200 million years old, since the first stars ignited in the primordial darkness, there are no stars anywhere in the cosmos. Think carefully about what this means. For approximately 100 trillion years, the universe has been a place of light. Stars have burned throughout the cosmos. Galaxies have glowed with the combined radiance of billions of suns. The universe has been alive with the nuclear fire that transforms hydrogen into helium and releases energy according to Einstein's famous equation. Generation after generation of stars has lived and died, creating the heavy elements, warming planets, making complexity and perhaps life possible. And now, all of that is over. Finished, complete. The darkness that follows is not temporary. It's not like night on Earth, which ends inevitably with the dawn. There will be no dawn after this darkness falls. The fuel for new stars is exhausted. The gas clouds that once formed stars have been depleted and dispersed. No new stars can form because there is nothing left to form them from. The darkness that descends after the last star dies is permanent. It will last for the remaining existence of the universe, however long that might be. What remains in this dark universe? The universe doesn't end when the last star dies. It continues existing, emptier and darker than before, but still present. Space still exists. Time still passes. Matter still drifts through. The void. What fills this lightless cosmos? Black dwarfs. Trillions upon trillions of black dwarfs. The cold and completely dead remnants of all the stars that ever lived and died across cosmic history. They're scattered throughout what were once galaxies, invisible and inert and utterly dark. Each one contains the mass of a star compressed into a sphere roughly the size of Earth, but they produce no light, no heat, no detectable radiation of any kind. They are the corpses of stars, and they will drift through the darkness for eons beyond counting. Neutron stars, the collapsed cores of massive stars that exploded as supernovae billions or trillions of years earlier. These objects are smaller than black dwarfs, but even denser, among the densest objects in the universe, short of black holes themselves. A neutron star might be only 12 miles across, but contain twice the mass of our sun, compressed until atomic nuclei merge into a sea of neutrons. When young, neutron stars spin rapidly and emit beams of radiation as pulsars. But by this late era, they've long since slowed their rotation and cooled to background temperatures. They're dark objects now, detectable only by their gravitational influence on anything that passes nearby. Black holes. When the most massive stars died in the early universe, they left behind black holes, regions of space where matter has collapsed so completely that nothing can escape, not even light. When galaxies collided over billions of years, their central supermassive black holes eventually merged, growing ever larger with each cosmic collision. By this late era, the universe contains black holes of various sizes, from stellar mass black holes just a few times the mass of our Sun, to supermassive monsters containing billions of solar masses, the merged remnants of countless galactic cores. These black holes are the most massive individual objects remaining in the universe, planets. Many planets have survived the deaths of their parent stars, still orbiting the black dwarf remnants or wandering freely through space after being ejected from their systems by gravitational interactions. Some might still harbor tiny amounts of residual heat from their formation or from radioactive decay in their cores, but most are frozen completely solid, dark balls of rock and ice drifting eternally through the void, their surfaces colder than anything we can experience on Earth. Debris, asteroids, comets, dust particles, the scattered detritus of star formation and planetary evolution accumulated over 100 trillion years. None of this emits any significant light. It simply drifts, cold and dark, through the emptiness between the larger objects. The universe in this era is not perfectly dark. There are still rare occasional sources of light, brief flickers against the eternal blackness. When two black dwarfs happen to collide, their orbits decaying over vast timescales until they finally merge, the collision can produce a brief flash of light and heat. When matter falls into a black hole, it heats up tremendously and glows brilliantly before vanishing forever beyond the event horizon. When two neutron stars merge after spiraling together for billions of years, they produce a kilonova, a brilliant explosion that briefly illuminates the surrounding space. These events are incredibly rare in this era, separated by enormous gulfs of time and space. They might happen once in a galaxy every trillion years, or even less frequently. But they do happen occasionally, unpredictably, brief sparks of light in an otherwise dark universe. There's also Hawking radiation to consider. According to quantum mechanics, black holes are not perfectly black. They slowly evaporate over time, emitting tiny amounts of radiation through a process discovered theoretically by Stephen Hawking. This radiation is incredibly faint, far too weak to illuminate anything or warm any surface. A stellar mass black hole would take approximately 10 to the 67th power years to evaporate completely through Hawking radiation. That's a 1 followed by 67 zeros. A supermassive black hole containing 1 billion solar masses might take 10 to the 100th power years, a Google of years, to evaporate. These timescales are so incomprehensibly vast that the entire 100 trillion year stelliferous era seems like nothing in comparison. The universe has been producing starlight for less than 1/1,000,000,000th of the time it will take for black holes to evaporate. The age of stars, which seemed so long to us, is actually a brief flash at the very beginning of cosmic history when measured against what follows. But even the evaporation of black holes is not the final chapter. On truly extreme timescales, matter itself may be unstable. According to some theoretical models, protons may eventually decay. The protons and neutrons that make up ordinary matter, the stuff of black dwarfs and planets and frozen debris, are thought to be stable. But some theories of particle physics suggest they may have an extraordinarily long but finite lifetime. If protons decay, then on timescales of perhaps 10 to the 40th power years, ordinary matter will gradually dissolve. Black dwarfs will slowly evaporate as their constituent protons decay into lighter particles and radiation. Planets will fade. Every solid object in the universe will eventually dissipate. If proton decay occurs, then even the corpses of stars will not last forever. The black dwarfs, which seem like they would drift through eternity, will gradually dissolve into nothing. The universe will become even emptier, containing only black holes, dark matter, and dispersed radiation. And after the black holes evaporate, after proton decay has claimed the last ordinary matter, what remains? Electrons and positrons, slowly finding each other across the vastness of space and annihilating. Photons stretched by expansion to wavelengths larger than the observable universe, perhaps dark matter particles, whatever they are, drifting through a void so empty that the average distance between particles exceeds the size of what we now call the cosmos. This is the ultimate fate of everything. Not a dramatic ending, but an endless fading. Not a bang, but an eternal whimper, growing ever quieter, ever emptier, approaching but never quite reaching absolute nothing. The last star is not the end of the universe, but it is the end of the universe as a place where anything interesting happens on timescales that matter to beings like us. After the last star, the cosmos becomes a waiting room with no appointment scheduled. The waiting will continue, effectively forever. So what does all this mean? Why does the last star matter to us, living as we do in the relatively early universe? It matters because it represents the end of something extraordinary, something precious, something irreplaceable. For approximately 100 trillion years, the universe will be a place where light exists, where energy flows from hot regions to cold regions, where complexity is possible and entropy can be locally decreased. The stars make this era special and unique. They produce the light that warms planets, the heavy elements that build rocky worlds, the energy that could support the emergence and evolution of life. When the last star dies, that era ends forever. The universe continues existing, but it becomes a fundamentally different kind of place. A cold, dark, static place where nothing much ever happens, where change becomes vanishingly rare, where the possibility of complexity and life has been extinguished, along with the stellar fires. The universe transitions from a place of potential and activity and possibility to a place of endless, empty, silent waiting. Waiting for nothing, because nothing is coming. The last star is the final ember of the cosmic fire that began with the Big Bang. It's the last representative of the age of stars, the final carrier of a torch that has been passed from stellar generation to stellar generation for 100 trillion years. When it dies, when that torch finally goes out, an entire era of cosmic history ends forever and will never return. And here's what I find most profound about contemplating this distant ending. Right now, today, you are living in the age of stars. You exist in what might fairly be called the golden era of the cosmos, when the universe is filled with light and warmth and energy and the possibility of life and consciousness and meaning. You were born on a planet warmed by a star, made of atoms that were forged in the cores of earlier stars that died billions of years before our sun was born, part of a living biosphere that has evolved and complexified over nearly 4 billion years. This is not normal. This is not the default state of the universe. For most of cosmic time, after the stars die, the universe will be dark and cold and empty of life. The era we live in is brief and precious and extraordinary. 100 trillion years might sound like an almost infinite span of time, but compared to the eternity of darkness that follows, it's nothing. A flash of light in endless darkness. A brief flicker of warmth before eternal cold. We are living in that flash of light. We are part of that brief flicker of warmth. Every star you see in the night sky is a miracle, a temporary violation of the darkness that will eventually claim everything. Every sunrise is extraordinary, a daily reminder that we live in an era when such things are possible. Every moment of warmth and light and life is a gift from the cosmos, a brief exception to the universal rule of cold and darkness and silence. The last star doesn't diminish this truth. If anything, it makes our existence more meaningful. Knowing that stars are temporary, that this era will end, that the light will eventually fail, gives our existence a context it would otherwise lack. We are here, now, in the age of stars. We should appreciate that privilege. We should marvel at that look. We should treasure every photon of starlight that reaches our eyes. And there's something else worth contemplating. The last star will exist in part because of stars like our Sun. The heavy elements in that final red dwarf, the trace amounts of carbon and oxygen and iron that will be mixed into its hydrogen fuel, were created by earlier generations of stars. Stars that lived and died billions of years before the last star was born. Stars that exploded as supernovae and scattered their enriched material across space. In a very real sense, our Sun and stars like it are the distant ancestors of the last star. Their deaths, their contributions to the cosmic cycle of stellar evolution, helped make the last star possible. We're connected to the last star across 100 trillion years of cosmic history. The same physical processes that created our Sun, that created our planet, that created us, will continue operating until the very end. The universe follows the same rules everywhere and always. The last star will burn using exactly the same physics that powers our Sun today. When you look up at the night sky, you're looking at stars that will die. Our Sun will die in about 5 billion years, swelling into a red giant and then fading into a white dwarf. The bright stars of Orion will die in mere millions of years, exploding as supernovae. Even the dimmest red dwarfs visible through powerful telescopes will eventually die, after trillions of years of patient burning. But for now, they shine. For now, the universe is filled with light. For now, we exist to witness it. That's what the last star teaches us if we're willing to learn. Appreciate the light while it lasts. Marvel at the warmth while it endures. Treasure the existence of stars while stars exist. Because one day, in the unimaginably distant future, the last star will flicker and fade. The nuclear fire that has burned since the universe was young will finally go out, and the darkness will last forever. But not tonight. Tonight, the stars still shine. Our Sun still rises each morning. Life still fills our planet with complexity and beauty and meaning. The age of stars continues, and we are here to witness it. Go outside if you can when the sky is dark and clear. Look up at the stars that are still burning. See the ancient light that has traveled across the void to reach your eyes. Remember that you are made of their atoms, warmed by their light, part of their ongoing story. And remember the last star. Somewhere, somewhen, it will burn as the final point of light in an otherwise dark universe. The last proof that the cosmos once blazed with fire and warmth and the possibility of life. The last star to ever exist. The universe is vast and ancient and will persist for incomprehensible eons after the last star dies. But right now, in this brief and precious era, the stars still shine, and you are here to witness them. That is a privilege beyond measure. The age of stars will end, but it has not ended yet. And while it lasts, we are part of something magnificent. Good night. And may you always appreciate the light of the stars while they continue to burn.